Hello. Good afternoon, everyone. I'm happy to welcome you to the afternoon session about performance modeling. Our first speaker is Jean from ETH Zurich, and please take the stage.
All right, so hello everyone for being here. So my name is Siyuan Shen, and I'm excited to share my work conducted in collaboration with Samsung Semiconductor. Although here Bob is no longer in Samsung, he's now working in HPE. So the topic that we worked on was assessing network latency sensitivity and tolerance of HPC applications, leveraging linear programming as a key analytical tool. So as we all know, memory and communication walls are a big problem nowadays in the world of HPC. And this plot here shows the evolution of speed of the compute hardware and the bandwidth of DRAM, as well as different types of interconnect. And as we can see in this plot, although the speed of both compute hardware and data movement are growing exponentially, the gap between them just kept widening. And this signifies the existence of an imbalance between compute and data movement. So on the memory side, the advent of HBM and 3D stacked memory can alleviate this problem. However, the communication wall is much harder to break. And the reason is that as network bandwidth grows, the bit error rate also goes up when transmitting data on the physical layer. And as shown in all of these papers and articles, to reduce the bit error rate to the point that it satisfied the stringent requirement of the new network standards, we will need to have stronger and more complicated error correction mechanisms. And using these more complicated error corrections will in turn increase the network latency, in some cases by microseconds per packet. Therefore, it will be very crucial for network engineers to understand if the performance of HPC applications will be impacted by the new upcoming network standards. Now, to answer this question, first we have to understand whether there actually exists a difference between the network latency tolerance of HPC applications. So here I present three applications from three representative domains. So we have MILC, which is a quantum chromodynamic simulation that is known to be sensitive to network latency. And then we have LULESH, which is very popular HPC benchmark. In the end, we have ICON, which is a weather and climate simulation. So on the y-axis, we have the runtime of these applications, and on the x-axis, we have different amounts of latencies. And as we can see that as latency increases, we see slowdowns in these applications. And now we show the different amounts of slowdowns with these colored regions, right? So these regions represent different amounts of slowdowns. So the green regions represent how much latency we can absorb before the application slows down by 1%, and the orange region 2%, while the red region 5%. So the way to interpret this is that, for example, MILC can absorb 4.8 microseconds of latency before observing a 1% slowdown. And in the end, at the bottom, we see that ICON can absorb a whopping 150 microseconds of latency before being slowed down by 1%. So what we can claim here is that different applications, due to their inherent algorithms and communication patterns, have vastly different latency tolerance, and understanding these differences would be extremely relevant for designing new systems and for mapping workloads. Additionally, another important use case would be evaluating and comparing applications' latency tolerance under, let's say, different network topologies, and, well, if we have different implementations of collective algorithms. So the question is, well, how do we achieve this, right? So how do we measure the latency sensitivities? Well, the first way is that we can construct very detailed performance models, but this would require a very deep understanding of the behaviors and the source code of the algorithm and the application. So this is rarely done in practice. And the second way to do it would be simply artificially inject latency into these applications and run them either on hardware, on real systems, or with simulations. So to inject latency into hardware, we would either procure new ones, or we would modify existing ones. But both of the options are quite inflexible and hard to achieve on a large scale. And during our experimentation, we also noticed that adding the sleep function in software does not yield accurate result because we're increasing the computation of the application instead of the network latency. And the details of this and why this doesn't work out are explained in our paper. So with simulation, it's easier to inject latency into the simulation, but the problem is that it's really, really time-consuming and expensive to run, especially for large applications on a large scale. So the fundamental problem of both of these two methods is that they would require extensive parameter sweeps, meaning that, okay, if you want to determine how much of an application, how much latency an application can absorb before observing, let's say, a 10% slowdown, you will need to run the application many times in order to pinpoint this. While our new method is able to do it very efficiently and directly. So here, let me present our toolchain, which is called LAMP, that stands for LogGP and Linear Programming-Based Analyzer for MPI programs. So we're going to start with MPI programs. So hopefully everyone here should be pretty familiar with MPI programs. And we trace them with the help of the PMPI interface. So afterwards, we obtain the MPI traces that record the list of operations as well as the signatures of these functions and the timestamps associated with them. And afterwards, we convert these traces into execution graphs, which I'll explain later in a bit more details. So these are done with existing tools. For example, we trace this with liberalprof, and we generate the execution graph with a tool called SCADGAN. So our innovation comes in the form that we convert the execution graphs into linear programs. And by parameterizing them with a performance tool called NetGauge and solving these linear programs with linear programming solvers, what we are able to obtain is going to be a list of different metrics which can be very, very useful for performance engineers and software engineers. So I'll start by talking about the left side of my toolchain. And here, to start, I want to sort of explain what the LogGP model is, right? So the LogGP model is one of the most effective ways to model computation and communication in a parallel system. So there are several parameters that are involved in this LogGP model. So to start, we have P, which represents the number of processes. So in this example, we're going to see 3 processes. And so we see that process P0 performs a send to process P2. And in this case, we have another parameter O, which is associated with the CPU overhead of both sending and receiving. And in the middle, we have the parameter S, which specifies the size of the message, and we have G, which is a get per byte, and you can also treat it as the inverse bandwidth. So when we multiply them together, S minus 1 times G, that's going to give us the bandwidth cost of sending a message. So on the other hand, we also have latency, which is represented by this letter L. So this is quite important because this is what the work is going to be focusing on. So the total cost of transmitting a message in the network can be represented by this expression, L plus S minus 1 times G. So here, I want to demonstrate with an example of how exactly we convert traces into execution graphs with the help of a space-time diagram. So on the left side, we have the MPI traces, right? So we see that we first start with MPI init operations that have these timestamps T0 and T4 associated with them. And we perform MPI send on rank 0, right? So the send operation is marked by timestamp T1 and T2 that marks the start and end of the MPI send operation. So what we can deduce in this case is the amount of computation that has happened between MPI init and MPI send. This can be represented by T1 minus T0, right? So, and correspondingly, we add a vertex C0 to the execution graph to represent this computation. So here we can do the same thing to receive on rank 1, right? So we can deduce that the computation can be represented by C2, and we add a vertex to the execution graph. And in the middle, we perform the send, right? So we start actually sending across the network, and the send operation and the receive, send and receive can be represented by the red vertices S and R. So we add these vertices to the execution graph. You also add a nudge connecting them, labeled by the cost of sending. That's according to the aforementioned LogGP model, it's going to be L plus S minus 1 times G. And in the end, we perform MPI finalize that has a timestamp T3, and we add another vertex, assuming an eager protocol is used, of course. And we also perform MPI finalize on rank 1, and we add another compute vertex to the end. So this is how we convert execution graphs convert traces into execution graphs for synchronous communication. So now I also have an example of how we convert execution graphs for asynchronous communication, specifically for I send and I receive, right? So what we see here in the graph is that the only difference is that we have 2 paths leading out of vertices C0 and C2 to represent the fact that computation and communication can happen in parallel. They can be executed simultaneously. And in addition, in our work, we decompose collectives into individual sends and receives according to predefined algorithms provided by the user. So with this, we're able to take into account all sorts of different types of MPI operations and deal with all kinds of MPI programs. So now we formally define, we get to the sort of the meat of the project, is that we define natural latency sensitivity formally as dt over dl. So we have t here, which represents the runtime of the application, and l that represents the latency as shown in the LogGPS model. So what this lambda term actually tells us is how much the runtime of an application changes as the latency changes, right? So here, to help make this concept easier to understand, we'll explain with a very simple toy example. In fact, this will serve as the running example that we'll use throughout the presentation. So as we can see here, there are 3 possible paths in this execution graph. And the runtime of this application will be the maximum of the cost of all the paths, which in other terms is going to be the critical path of the execution graph. So in this parentheses, we highlight the expressions of the cost of each one of the paths in different colors. So we have the first pass, the second one, and the third one. So what we can do is that we can substitute the computations and different LogGPS parameters, actual values, into this big expression. And what we're going to end up with, after simplifying, so what remains in these parentheses will be the cost of 2 of the paths, right? So it's going to be the orange path, and it's going to be this purple path. So now if we plot the runtime of the application against L, we can see that the result is going to be a piecewise function. That's the solid part is going to be the actual results. So now if we plot dt over dl, on the other hand, we see that it first starts from 0, and it's going to jump to 1 at the point of intersection. So here we show that the latency sensitivity of this application can actually be represented by a step function that's made of 2 pieces. And this point of intersection is extremely important for us because this is a point at which the critical path actually changes. And here we notice something very important during our investigation, which is that the number of messages along the critical path would determine the natural latency sensitivity. So this is quite intuitive, right? As we increase the number of messages along the critical path, this means the application is going to be more sensitive to the network. So to generalize, what we have is that we can represent t as the maximum of the cost of all of the paths in a graph. And what if we plot it now? So if we do this for any general application, what we're going to discover is that the natural latency and how it's plotted against L can be represented by a step function that's made of a lot of pieces like this. And the point at which the critical path changes, they're going to be called the critical latencies. And this curve is, we call it the latency sensitivity curve. So this curve is important because it shows us all the latency hiding potentials in an application, right? Because intuitively, the larger the distance between the critical latencies, the higher the potential it is for the application to hide its latency. So now we also notice that the value of L, the natural latency, has a second order effect on this sensitivity, because as L gets larger, this application also becomes more sensitive to it. So the next question to ask is that how do we obtain this latency sensitivity curve analytically? Well, we can use a naive method, which requires finding the path of all of the paths in a graph. And this is fundamentally intractable because we all know that as the number of paths grows exponentially with the number of vertices in the graph. So we've come up with the dynamic programming algorithm to deal with this. But during our experimentation, we noticed that with dynamic programming, this is also not scalable because even for smaller graphs with fewer than 500,000 vertices, it consumes a lot of memory and takes a long time to run. So in the end, inspired by the simplex algorithm, as well as the fact that linear programming is used extensively to solve graph problems, we have developed linear programming as a final solution to find the latency sensitivity curve and to obtain all of the other interesting metrics. So here I want to demonstrate the connections, let's say, between linear programming as well as the graphs. So how are they connected? So we start with a running example, and we developed a linear time algorithm to convert this mechanically, this execution graph, any execution graph, into its corresponding linear program. So here, the detail of this algorithm is skipped due to time limit, and you can find the details in our actual paper. So we see the end result is going to be a linear program that has an objective function and 4 constraints with 3 decision variables. So in order to make this graph, well, this example easier to visualize, what we're going to do is that we want to substitute the variable y1 into the last constraint. So in the end, we're going to end up with a linear program with 3 constraints and 2 decision variables that are very easy to visualize on a 2D plane. So now to demonstrate the connections actually between graphs and linear programs, we're going to start with the constraints from the previous slide. And so one thing that we would really want you to take note of is that constraints in a linear program are nothing but alternative representations of path in a graph. So here I show with different colors the constraints and their corresponding paths in a graph. And I also visualize the constraints themselves in the plot on the right. So we add constraint L is larger than or equal to 0.5 to say that we're interested in the result when the latency is exactly 0.5 microseconds. So what we can see here is that the white region is going to be the feasible region. And if we solve for the objective function and minimize t, we find that these 2 constraints are going to be on the border of the feasible region. And their intersection determines the objective value, which is going to be the runtime of the application. So I know that the math might be kind of boring and whatnot, but there are 2 extremely important takeaways that we really want to emphasize. So these are the things that should be remembered from this talk, which is that, first of all, solving the linear program will find the critical path directly. And so in simple non-mathematical terms, what we can tell is that the critical path simply can be determined from the constraints that define this objective value. So in this example, we see that the constraint t is larger than L plus 1.115. This is on the border of the feasible region, and it determines the objective value. So now we see that its corresponding path is going to be the critical path. And the second takeaway here is that the objective value of the linear program directly gives us the runtime. So we say that linear programming can be used for estimating the runtime of an application given different, let's say, LogGPS parameter values. So here I also, I want to talk about the types of metrics that we can obtain from doing this linear programming analysis. So the first metric, well, is going to be this linear sensitivity curve that I mentioned before. So how do we obtain the sensitivity curves more efficiently than conventional methods? So we solve this linear program, and we're going to get 2 metrics out of it. So the first metric is going to be this natural latency sensitivity, because as I mentioned, well, if you solve it, you get the critical path. And we know that natural latency sensitivity is nothing but number of messages along the critical path, so we're able to obtain this directly. And the second metric that we obtain is going to be the range of feasibility. So what is the range of feasibility? It's given by 2 bounds. So it's going to be given by two values that define an interval within which the critical path would remain the same. So here I have an example of how the runtime of an example application would change against increasing latency. So here it's made of 3 linear pieces. And let's say if we solve the linear program at this specific point when the latency is equal to this big L, then after solving it, we will find the regions within which this delta L, dtdl is going to be the same within this bound, right? So, and these bounds are going to define the critical latencies for us directly. So what this implies is that we would no longer need to sweep across all of the latencies in order to find the sensitivity curves, because solving this linear program would provide us with information around the regions around the next to the solutions. So this is how we're supposed to optimize compared with the conventional methods. And the second metric that I want to mention is this natural latency tolerance, which is the blocked color regions that I showed at the start of the presentation, right? So in this case, how do we obtain this is that we want to make 2 changes to the original formulation of the linear program. So the first change that we want to make is to change the minimization problem to a maximization problem. And this specifies that we want to actually find the maximum tolerable L. And the second addition that we want to make is that we want to add another constraint to specify exactly the maximum allowable execution time of the program. And so after visualizing it, so after visualizing these constraints, we're going to see that the feasible region, the white part, is going to be capped. It's going to be upper bounded by this newly added constraint. And so what happens after solving it is that it's going to give us the maximum tolerable latency beyond which the runtime will exceed the predefined threshold. So as an example, let's say if we know the baseline runtime of an application and we don't want its performance to degrade by more than 10%, and we want to find the maximum latency that it can absorb in this case. So in this specific case, you can use linear programming to find exactly how much latency the application can absorb before being slowed down by 10%. So besides these metrics that we have just introduced, our toolchain can also perform many types of analysis. To list a few, we have bandwidth sensitivity, bandwidth tolerance, all types of critical path analysis, and also supports heterogeneous network and network topology analysis. So as long as we can represent parameters that you are interested in with decision variables in a linear program, we'll be able to produce all kinds of interesting metrics. So the takeaway here is that LAMP, our toolchain, is extremely versatile, and it has a lot of potential applications out there that are yet to be discovered. So here I want to show how fast our toolchain is compared with some of the state-of-the-art simulators. So here we use LogGPS, which is one of the most efficient and fastest open source network simulators. We compare this against our toolchain, which uses Gajbe as a linear solver. So here we first present the results from LogGPS across a range of applications and benchmarks and see the runtime of LogGPS. Note that it's in log scale. And now we compare this with our toolchain, and we see that on average, we achieve a 4 to 100 times speed up compared with one of the fastest network simulators out there. So this speed up can mainly be attributed to the fact that linear solvers nowadays can remove redundant constraints with the use of advanced pre-solve algorithms. So then we validated our toolchain with injection experiments of real applications on real systems. So here we performed we measured the runtimes from 7 applications and compared them with the predictions from our toolchain. And due to space constraint, I'm only showing 2 here. So there are 2 rows. So the first row shows the result from LULESH. The second row shows the result from ICON. And each row also has 2 parts. So the first part shows the runtime and how the runtime varies as the latency increases. And the second half, the bottom half, is going to show the latency sensitivity curve that we mentioned. So now, so in a real system, it took 45 hours around to obtain the data. And with LogGPS, it would have taken around 14 hours to get the results. However, with our toolchain, it took only around 5 hours, including tracing and pre-processing time, to obtain the same data. And now we show how the runtime prediction of our algorithm actually is compared with the real runtime. And we see that the relative root mean square error is below 2% across the board for all of the applications. And this shows that our toolchain is fairly accurate. And now by showing the latency tolerance regions, we can also tell, and also with the help of latency sensitivity curves, we're also able to tell in which intervals the applications are more sensitive. And in the end, we also perform a case study on ICON, which is the weather and climate simulation used by a lot of the European weather agencies. So we compare the results of the performance impact of 2 of the ORDUCE algorithms, which namely are recursive doubling and ring. So in the first row here, we show the results from recursive doubling, and in the second row, we show the results from the ring algorithm. And after showing the latency tolerance regions, we're able to make the conclusion that ICON's performance becomes much more sensitive to network latency when the ring algorithm is used. So in this case, we showed an example that demonstrates the potential of using LAMP, our toolchain, for designing and optimizing collective algorithms in real applications. So to conclude, in this work, we developed the LAMP toolchain, which is based on the novel idea of using linear programming to perform sensitivity and performance analysis of MPI applications. We formally define the various metrics such as latency sensitivity and tolerance. And we also want to mention that LAMP is the first tool out there to compute these metrics analytically and efficiently. And we also validated our toolchain on a range of different applications and benchmarks. So There are many, many more results that we haven't had the time to show here, such as bandwidth sensitivity and topology analysis, and you can find all the other results in the paper. And if you're interested in using our toolchain, it is completely open source and can be accessed on GitHub. And that's the end of my talk, and thank you all for listening.
So thank you for this great presentation. I see questions already.
Very good work. I'm puzzled by something. Can you go to slide 21, the one that has that red? Yeah. I thought you're going to see, in your method, you're going to see either steps for or straight line for the curves, depending on when you switch from one, like k latencies to k+1 latencies and so on. And instead, I see a little more continuous curves, and also the slope. If you look at the bottom half of the top curves, the slope doesn't monotonically increase. It seems to decrease sometimes. I kind of don't understand.
So all of this, okay, so to answer your first question, so why don't you see this kind of discrete kind of steps? So in this case, it's due to the sort of the resolution, right? So we're plotting this on a resolution of nanoseconds, essentially. So that's why, like, if you sort of zoom out, you see everything as sort of continuous. But in the end, they're in fact discrete. And to answer your second question, so why do you see the slope changes? It's due to the inherent communication pattern of icon. So there is a lot of latency hiding techniques that are used in some of these HPC applications, by performing overlap of communication and computation with, the asynchronous communication, you're able to hide some of the latencies. And that's what the aim of our work is gonna be, right? So it aims to find, with the sensitivity curves, all the latency hiding potentials that are in there. So that's why it's not going to be purely linear for all of them. And that's what makes it interesting, right? If you have just, application that runs whose runtime runs linearly, then it's not gonna be interesting to analyze.
Yep. Okay. And I think more complex wildcard receives probably are not easy to model with this method. Simple I receives will be, but when the code path changes, depending on the message processing, that's going to be more difficult.
Yes, but with linear programming, you're able to find how these critical path changes very efficiently. So it's going to be easier to model.
Okay.
Yep.
All right, will do.
So we do have time for one more question.
Great talk. So one of the assumptions in this talk is that the latency sensitivity is proportional to the number of messages along the critical path. So does that still hold true if you have some sort of overlap that you can get in the path? So if I have two steps in the path and one message is here and one message is there, so will this still hold true?
This would work. Yeah, so with how the graphs are constructed, so this would take that into account. Yep.
Okay, thank you.
Are there any further questions? Oh, see one in the back.
Thank you for the talk. I wonder, like, considering your network model, whether maybe you didn't show this or I missed it. If you have congestion, how is that something that's taken into account? Because in the equations, I see that there's a deterministic assumption on the time that a message is going to get. So if you have replace, if you have incast, I wasn't seeing that being modeled.
So that's a very nice question. So this is actually one of the limitations of our tool. So we know this is something that it doesn't really take into account, network congestion. And in the next version of the tool, we're sort of trying to use another model. We will try to use another model to take this into account. But very nice question. Thank you.
Okay, so let's thank our speaker again. Thank you.